Good morning, everybody. It's a great pleasure to introduce Vanessa Hill. Vanessa did her PhD in Meudon, Paris, with Monique Spitt on chemical abundances of supergiant stars in the LMZ. After that, she moved to São Paulo in Brazil for a postdoc. Then she was an ISO fellow at ISO Garking, where she was essentially taking care of the US commissioning and operations for her duties, apart from her scientific work. And then after that, she got a permanent position in Paris, right, in Meudon. And then in 2008, she moved in Nice, always in France. She's the leader of the Galactic Archaeology surveys that are being planned for the WIV spectrograph that will be mounted at the William Herschel telescope in the very near future. And today she will tell us about the chemical evolution of the Milky Way and satellite galaxies.
This is better? Yeah, I can hear the echo. So our own Milky Way and also the very interesting dwarf galaxies that are orbiting around the Milky Way and that tell us a lot about really the processes that preside to the chemical evolution of galaxies. And what I will try to do today is to basically concentrate on two different things. After some global context and introduction, I will concentrate on a few things of dwarf spheroidal galaxies, and the approach that I will take is to try to use one of the dwarf galaxies that is the most studied probably around the Milky Way, which is Sculptor, and use everything we know about Sculptor to look at chemical evolution from a completely observational, almost empirical point of view, and to try to figure out whether we understand what we see and whether it makes sense with the kind of textbook knowledge that we have about chemical evolution. And the second part of my talk will be telling you a bit more about what using Gaia data in coordination with some spectroscopic surveys can tell us for our Milky Way and its neighbors. And I will concentrate, of course, to this audience on telling you a bit more what WIV is planning to do in this respect. So a little bit of global context first. As you very well know, the formation of galaxies is currently seen within the global context of cosmology. And we have this beautiful lambda CDM concordant model that is very successful in reproducing a lot of the very wide, large-scale structures of the universe, from the CMB itself to the formation of large-scale structures, to the formation of clusters of galaxies, and the formation of galaxies in a context where smaller structure form first and then assemble in a complex way that is traced also with these nice filamentary structures to assemble the big galaxies we see today. And because we think that galaxies form like this, we do expect that in today's Milky Way-like galaxies halo, we should still see the traces of the history of how the galaxy was assembled. This concordant model is really extremely successful at large scales. However, at the smaller scales, it suffers a number of issues. And I've put here a few which are directly linked to dwarf galaxies. One of probably the most well-known problems of lambda CDM at the small scales is the number of satellites that are currently detected around galaxies compared to what is predicted from the simulation of dark matter halos. And so you see here the simulations. So in in dotted line is around a Milky Way-like galaxy. And you see the number of satellites is supposed to increase a lot with decreasing mass of the satellite. And these are the observed satellite numbers. This I've taken on purpose a very old instance of this problem, and since then the number of very low mass satellites of the Milky Way has grown, but the difference between the predictions and the observation is still very large. And I like this picture because it shows that at galactic scale you have this big problem, whereas at galaxy cluster scale, which is the full line here and the dots with the error bars for the Virgo cluster, on the other hand, the numbers are pretty much what you expect. So it's really something that has to do with what is happening at the lowest scale with galaxy evolution. There is another instance of the problem, which is the too big to fail problem, and that you can see here. So basically, the predictions for galaxies of given luminosities are much more massive than what you observe at that given luminosity. And so, simulated halos tend to be denser, more massive than the observed ones. And one of the other problems that I've also illustrated here is that also the shape of the potential of galaxies is predicted to be cusped in dark matter halo simulations. So the famous NFW profile here, this thing, whereas it tends to be observed to be a bit flatter, what is called chord galaxy profiles. And last but not least, we also tend to observe satellites around galaxies around the most, so did I go the right way? Yep, okay, I can, sorry. Before going to the planes of galaxies, everything that I've said before has been discussed extensively, of course, in the literature in the last 20 years. And a lot of it actually can be, if not solved, at least alleviating by not looking only at dark matter-only simulations, but also including the effects of baryonic physics and baryons in these simulations. And this alleviates a lot the problem. One of the examples of this is the missing satellite problems. Is it the fact that the smallest satellites are only dark matter and never manage to make stars and become luminous? Is that the reason why there are so many more that are predicted than what you observe? That could be a very good reason. There can be also other reasons that are also completely linked to the baryonic physics. For example, star formation could be prevented at the lowest masses by a number of effects. For example, reionization that could strip gas. UV radiation could inhibit the star formation. There can be also some effects of the supernova feedback, changing basically preventing star formation. And similarly, the problem of the core and cusps, there is clearly a retroaction of how baryons distribute in the potential to how the dark matter actually distributes within the potential. So you can also alleviate the problem of, or you can make cored galaxies just by including the effects of baryon and their retroaction on the dark matter halo. And I chose this nice picture because I think it's a PR thing done by the Eagle simulation group on a local group thing. And the funny thing is they've cut basically their image in two. On this side is the image of what they see if they look at the dark matter distribution. And on this side, it's the exact symmetric, but looking only at the luminous matter. And this illustrates how much, indeed, if you only can look at the luminous matter, you are only uncovering a part of the complexity of the fine details that are seen in the dark matter simulations. So this is again illustrating that baryonic physics play a huge role in this thing. There is a last problem that I wanted to mention in this direction that also has to do with dwarf galaxies. Is that in the lambda CDM you don't expect to have, you expect fragments and gas and even galaxies to be accreted sometimes along filaments and things like this, but you don't expect this to actually form very thin planes of satellites around big galaxies. However, both in the Milky Way and in M31, this is what we seem to be seeing, that most or a large fraction of the satellites of these two galaxies seem to be in rather cold planes or very thin planes around the galaxies. And this is also something that is complicated to explain with lambda CDM. So to try to wrap this up, I mean, the idea that I'm going to try to bring forward that is very often called galactic archaeology is to try to understand really the relative importance of everything that shapes galaxy evolution from the point of view of the environment. So all the merging, all the external processes, both by mergers of existing subsystems or mergers of or gas accretion, and to weigh the importance of these processes versus the internal processes that are all baryonic and that can be migrations within disks, effects of the merging systems onto existing populations, etc. And this is really a question we try to answer, and in particular, the Milky Way halo is a very good place to try to understand the ratio between these two, or the relative importance between these two types of processes. And what I would like to argue here is that studying the dwarf galaxies around the Milky Way that today have survived, so which have not been accreted onto our galaxy, is something that is very important for two different aspects. One of that is indeed to understand what is the importance of the merging of these things by studying the surviving ones and try to see if we can set or define what are the signatures that we should be looking for when we are looking at the ones that would try to detect the ones that have been already accreted. And this is a bit what Elena was talking about yesterday about identifying what are the signatures that one should look for in the Milky Way to figure out where the stars came from. And the other important aspects of dwarf galaxies is that they give us a very nice way to investigate really the galaxy evolution. So looking at these systems as not isolated, but at least a full system, and look at the way they evolved, gives a lot of information on how this baryonic physics that we master very poorly happens at the smallest scales. And at the smallest scales, all of the mechanisms of galaxy evolution are going to compete at a very, very interesting ratio, one between the other. Most of it has to do with the fact that the global potential well is small. And so a lot of effects like galactic winds, like quenching star formation, like all of these things, supernovae feedback and so on, will have a large effect in these small potentials. And so the dwarf galaxies have these two interesting aspects to them, which is both try to see in them as survivors the trace of what we should see once they have been accreted, and to understand really the internal evolution of these systems at the smallest scales. And the global principle of what is called galactic archaeology is to make this very basic realization that a star, because of the way stellar evolution goes, low-mass stars live a long time. So stars that have been born at the very beginning of the universe, 13.7 gigayears ago, with a mass lower than 0.8 solar mass, should still be around today, because their lifetimes are longer than the life of the universe. And so using these as tracers of the assembly of galaxies is very powerful. Can be done both in spatial, by the position of stars. Sometimes it can tell us where they come from. An example of this is the beautiful Sagittarius stream in the galactic halo, where we see the accretion going on. Kinematics can help us much better, because even a satellite like this that showed something spatially very nice 1.5 gigayear after its accretion on the potential. After a few gigayears, the stars are all dispersed everywhere. However, their signature in the phase space, or in the velocity, is preserved. So it's basically a way of getting back this kind of signatures, but even when they are dispersed all over the galaxy. And finally, the chemical composition at their surface is also preserved, and this is very important because it gives us an indication of what the gas these stars were formed with was, and this is a direct trace of the history of the population. And an example of chemical signatures is given here by separating chemically the thick disk from the thin disk, and this is a very historical paper. This is the 2008 instance, but Furman started this work in 10 years before that, where you see that in the ratio of two elements that are an alpha element and the iron, as a function of the metallicity of the star, the two populations separate very nicely because they have had a star formation history that is very distinct. So the basic idea again, and I've stole this picture from Jerry Gilmore a while ago, which I think illustrates nicely what this whole idea of galactic archaeology in the context of Gaia is trying to do, is to try to enlarge the parameter space in which we can figure out the signatures that give the origin of the star. From the position on the sky, the parallax from Gaia gives a distance, so the position now in 3D, adding also the velocities, transverse velocities gives 5D. If you have also spectroscopy and a radar velocity, it gives 6 dimensions. And if you can add other information such as the chemistry, the ages, etc., it gives you even more dimensionality to your parameter space. So before I go back to our own galaxy and Gaia, I'd like to start with these dwarf galaxies in the local group. And so this is a nice view of the local group with the Milky Way and its suite of satellite galaxies, M31 and its suite of satellite galaxies. And what you see is that our local group is dominated by these 2 large spiral galaxies, some smaller galaxies such as M33, M32, 13 irregular galaxies, including the LMC, the SMC, etc., and 100 dwarf galaxies, dwarf galaxies, of which more than 50 actually orbit the Milky Way. And their masses are typically of the order of 10 to the 8 solar masses, so much lower than the 2 big spirals. So another view of the same thing, more schematic, where now the colors tell you what kind of dwarf galaxies are found where in the local group. And what you see is that the dwarf spheroidal galaxies, which are the ones that are today devoid of gas and have, as their name tells, some kind of roundish features in general, are all concentrated around, or almost all concentrated around, the centers of mass, so M31 and Milky Way. Whereas the irregular galaxies, that are those that still have gas and usually also some star formation ongoing, this is why they look irregular, they are found throughout the local group and preferentially far away from the centers of mass. So you see already that the very recent evolution of dwarf spheroidal galaxies might have been influenced by the galaxy they orbit, in the sense that probably the gas that they contain at some point was either expelled by the internal evolution, but also could have been expelled or tidally stripped by the host galaxy. Dwarf galaxies around in the local group exhibit an amazingly large variety of characteristics when you look at the color magnitude diagram that give you an idea of the star formation histories in these galaxies. And you see here each time the HR diagram and the corresponding star formation history. And in this instance, the beginning of the universe is here, and today is at the red arrow here. And what you see is that there is a lot of the dwarf spheroidal galaxies that have only 1 peak of star formation very early on in their evolution and nothing afterwards. And that's one example, that's Sculptor, that is orbiting the Milky Way. But you also have an example like Cetus that is much further away from any of the two big spirals, but still exhibits something pretty peaked in the star formation history. But you also have things that are much more extended. And this is the example of, for example, of Leo A, which has had some star formation very early on, but then has now and has had in the past gigayears a very large chunk of its stars formed. And you also have very weird things like Carina, where you can already see on the HR diagram that there are several sequences at the main sequence turn-off level that translate into very separated peaks of star formation. So this galaxy actually made stars very early on, then stopped, then made a lot, then stopped, then made a bit, then stopped. So I mean, this kind of behavior and the variety that you see among these galaxies really tell you that there must be a lot of different processes interplaying to, from galaxies that have globally the same total mass, end up with such different results in their stellar content. I couldn't resist actually showing this because it's the beautiful Gaia DR2 map here, on which the proper motion of each of the, in red, of each of the satellites have been depicted. And this shows you also how Gaia detects one of these small dwarf spheroidal galaxies, in this case Sculptor. And this is to introduce you to Sculptor. So Sculptor, we saw, is one of these typical dwarf spheroidal galaxies where all of the star formation history happened early on, doesn't have gas anymore. It's close to us, it's only at 80 kiloparsec. Is, as you see, close to the galactic pole, which means that there is very little foreground absorption in terms of reddening. And so it's really probably the easiest pick if you want to start with an easy galaxy to try to gather all the information you have about it. And indeed, it's one of the first targets that we picked in the DART collaboration. What we did is to do spectroscopy of, in pink here, of a lot of targets out to the tidal radius of Sculptor. At low resolution, and then in the central part, some spectroscopy at high resolution to have some more information about the detailed chemistry of stars. So, a little tour of what we know about Sculptor. So we know that its metallicity distribution is broad. It has a metallicity peak around -2. But it has stars really reaching between -1 metallicity all the way to the most pristine or the most primitive stars. We actually have detected in this paper probably still the record holder for a metal poor star in a dwarf galaxy at -4. -4 is 1/10,000th of the solar metallicity. So it's really a very, very metal poor star. So it means that Sculptor indeed has a whole population that within that peak of star formation of a few gigayears has managed to make stars of all metallicities between at least -4 and all the way to -1. What we also know about Sculptor is that there are, in fact, even if this system looks very nice, very simple, roundish, single big peak of star formation history and so on, still holds two populations. There is one older population, more metal poor, that is more extended on the sky, and one younger that is more metal rich and centrally concentrated population. And this is, I've chosen to illustrate here, which gives you the radial velocity of stars all the way to the tidal radius. Color-coded are simply stars separated by metallicity. The red ones are the more metal-rich stars, and the blue are the more metal-poor. And you see directly what I was saying. The metal-poor stars are more extended. The metal-rich ones are more concentrated. And what you also see is that the metal-poor population is hotter dynamically than the metal-rich population. So there's really two populations of stars coexisting within Sculptor. The current total mass estimate within almost 2 kiloparsec of radius is 3.4 10 to the 8 solar masses, and it's a galaxy that has been shown to rotate mildly. And I should say all of this is work by Giuseppina quite a while ago. Yes. No. I mean, look at the rotation, and here you have the. I didn't write the dispersion, but the dispersion is for the rich population the same order, for the poor population even stronger than rotation, like 1.5 times the rotation signal. So star formation history, I showed you already an older version of the thing. We've also, within the DART collaboration, obtained some very wide field, deep color magnitude diagram that were, in this work by Thomas de Boer, fitted simultaneously together with the metallicity distribution function that we measured from spectroscopy. And this is a way to get rid of possible degeneracies between ages and metallicity in the HR diagram. What it gives is a fit of the color magnitude diagram overall that is not necessarily better in the sense that the residuals are not necessarily much lower, but it ties completely together what you know from spectroscopy than from what you know from color magnitude diagrams. And these are the comparison of the two CMD. Don't worry, this is not residuals, it's just because the isochrones didn't contain the horizontal branch stars. And doing this, one retrieves basically a metallicity distribution from this fitting that compares by definition extremely well with the one that is observed from spectroscopy, and gives you also a star formation history that again, so this time, sorry, it's flipped. Today is here and the past is there with a big peak of star formation tailing off at younger ages. Now going into the chemical information that we have on this galaxy, I'd like to do a little bit of textbook reminder to everybody. I've plotted here 3 elements, or the ratio of 3 elements to iron as a function of iron. I've chosen magnesium, which is an alpha element, europium, which is an element that is made by neutron capture rapid processes, and barium that is also made by neutron captures, but can be made both by the rapid process or the slow process. What we know about the progenitors for these different elements is that supernova type 2, so core collapse supernova of massive stars, they produce a lot of alpha elements and they produce a bit of iron. Whereas supernova type 1a, they produce a lot of iron and no alpha whatsoever, or very little alpha. And because supernova type 2 are massive star, they come from massive stars, whereas supernova type 1a have a much longer time scale. You have a delay between the enrichment of these two things, giving rise to this high alpha plateau at low metallicities when only massive stars have had time to enrich the medium. And at some point there is what we call the knee, so the start of the decrease of this ratio when supernova type 1a's, after a certain delay, start to enter the chemical evolution. When you change in a galaxy the star formation history, or the efficiency in which the galaxy enrich itself in metallicity, you will change the position of the knee, because what determines the position of the knee is basically how metal-rich the galaxy has managed to make itself before supernova type 1a come in. So the supernova type 1a is a delay, so it's a time thing, whereas here we're not looking at time, we're looking at metal enrichment. So if you change the star formation of the galaxy, or the star formation efficiency in the galaxy, you will change the position of the knee. If you change the initial mass function in your galaxy, you will change the position of this plateau. And if you change something else in the galaxy that changes how much a galaxy is able to enrich itself by a given time, so it can be star formation history, but it can be also simply, if you lose the metals you produce by galactic winds, you will produce exactly the same effect of changing the location of the knee here. These two elements, yeah, okay, I can just say a word. The R process element is also made by massive stars, so you have exactly the same schema as above, of a plateau and then a knee because of the coming of the supernova type 1a. The barium is a bit more complex because at early times it has R process in it, and at some point also the S process that comes from intermediate mass star AGBs make the thing flatten out. Now, let's compare what it is in, and I should say the black points in the previous things were our own galaxy, disk, thick disk, halo, everything together. Now, if we compare our own galaxy with Sculptor this time, which is going to be in blue, and our galaxy in black, you see that basically the blue points don't fall onto the black points. So indeed, the chemical evolution of a small thing like Sculptor is not the same as a big thing like the Milky Way. On the left part, I've put an assortment of different alpha elements. Oxygen and magnesium are the ones that are the least produced in supernova type 1s and the more in supernova type 2. So this is where you see the most difference between the galaxy and Sculptor. And in all cases, what you see is that the knee is basically happening at much lower metallicity than it is in the galaxy. In the galaxy, it's between probably around minus 0.8 to minus 1, whereas in Sculptor, it's around minus 1.8 or minus 2. So definitely we know already from this that there is something very different in the star formation history and in the ability of this galaxy to retain its metals compared to what the galaxy can do, the Milky Way can do. This is now neutron captor elements. So I told you europium comes from the R process and barium from a mix of the two. So a way to determine where barium comes from is to take a ratio of the two. And you see that at low metallicities, basically, the barium comes only from the R process, and the ratio you expect for the R process only is given in green here. Whereas at higher metallicities, there is also a fraction of S process entering the game. And indeed, if you look back here, europium looks pretty much like an alpha element, as you expected, because the R process comes from massive stars. And the barium, on the other hand, increases significantly in that region before flattening out. And I've put here the metallicity at which we expect the S. We see the S process starts kicking in, and you see that indeed this is what explains the flattening of the ratio. Because we know a lot about Sculptor, and because we have done this exercise of doing the star formation histories, tying in the metallicity that we know spectroscopically, we can also turn the argument around and try to measure ages for individual RGB stars in that galaxy with a much better accuracy than if you would do it just by fitting random isochrones. So basically what we do is that we take the families of basically the star formation, the synthetic star formation history color magnitude diagram, and choose the age of the individual stars in there, given their measured metallicity, and given the fact that they have to come from the same family. And the result is that we managed basically to measure ages in a relative sense for these RGB in Sculptor to something like better than 2 gigayears for most of the cases. And so what we can do now is to look at the age metallicity relation using not abundance ratios, but really the time on the axis. And this gives you how the age metallicity goes for iron, magnesium, which is an alpha element, and barium, which is this R plus S process element. And so for metallicity, you see something that is very narrow. And we've color-coded here in different colors simply by different bins of metallicities that we've chosen to cover the part where the alpha elements are close to solar, the part where the alpha elements are on the plateau, and the zone around the knee and the alpha elements. And so you see for iron there is a very nice and narrow sequence. Same thing for an alpha element, the magnesium. But when you go to an element that comes from a completely different nucleosynthetic path, namely the R plus the the S process, what you see is that the dispersion blows up very significantly at the lowest ages. And this we tie to the fact that the R process source, so in this range, it's the R process making this element. And so what we take from this is that the R process source is something that is badly mixed around the galaxy, whereas the other elements are very well mixed within Sculptor. The other thing that is very interesting to look at is that we can actually time when this supernova type 1a started influencing or contributing significantly to the chemical evolution by looking at the ratio of magnesium of iron as a function of time this time, or age of the stars. And what we see is that this basically happened already 12 gigayears ago, in the sense the decrease starts very early. And so this is compatible with a delay by the supernova type 1As of the order of 1 to around 1 gigayear at most. We can also time the onset of the S process by looking at the ratio of the two. But admittedly, the number of points that we have here is so low that it's difficult to make a proper estimate. We can also look at things still very empirically and say, okay, if I look at abundance ratios now to an alpha element instead of the iron, I'm getting myself rid of the influence of supernova type 1As, meaning that any element that will be flat in that plot is made only by massive stars. And any element that will have a slope in that plot will have a contribution that is significant from another source that is longer lived than the massive stars. And if we do this, not surprisingly, the alpha elements, an element that like oxygen that we know has no contribution from supernova type 1As, is absolutely flat. And the other alpha elements have a small slope, which means that calcium, titanium in this case, have some contribution of supernova type 1As in them. Even if it's a minority contribution, it is there. We can do the same for the iron peak elements. So iron itself is in black here, and some other elements of the iron peak are here. And what you see is that there you have a huge slope, which is indeed because iron comes mostly from supernova type 1As. And I'm not going to go through all of these elements, but you can really trace back the slopes that you see here to confirm what we thought we knew theoretically from yields of supernova type 1As and supernova type 2s for each of these elements empirically. And I think this is a very nice thing to do. I should point out that the reason why it's interesting to do this in Sculptor rather than do it in our own galaxy is the fact that Sculptor had this one go of big star formation and then nothing, which means that once these few gigayears in which it made stars is over, then it's only the supernova type 1As or the longer-lived things that contribute. The massive stars don't contribute anymore. And so it makes it the right environment to actually trace these contributions by the other sites, in particular supernova type 1As. And the same thing holds now for the heavy elements, where you see europium is perfectly flat because it comes only from massive stars. Barium has this huge slope because it comes a lot also from the S process. So enough of Sculptor. I think I told you more or less an empirical view of what you can get from studying the chemical evolution of a galaxy like Sculptor. Let's go back a bit more to the putting things in context. Sculptor is not the only dwarf galaxy we have around us. And now if I look at the alpha elements over Fe as a function of metallicity, same space as before, but each dwarf galaxy is a different color. You see that not all dwarf galaxies are like Sculptor either. they each have their individual locations. And in this case, in red you have Sagittarius, which is more luminous than Sculptor. Fornax, that has many more young stars than Sculptor. Sculptor here is in green. Carina, that has the funny several peaked star formation history, is in pink. And in orange, you have Sextans, which is probably the lowest luminosity star of this whole sample. And what you see, in fact, is two things from this plot that I'd like you to take away. First of all, if you go low enough in metallicity, you always end up on the plateau. So there is always an early phase in these galaxies where the abundance ratios are the same as in the Milky Way halo in the mean. And this tells us that the IMF of the high mass part of the IMF, which impacts the level of this plateau, cannot be very wildly different between these environments. And then the second thing that you can see is that the location where the knee happens in these different galaxies is not the same. And if you rank them by the position of the knee, what you end up seeing is that it's in fact a luminosity trend. And this is very nice because it means that among the scaling relations that we know of dwarf galaxies, I guess the most well-known one is the fact that as the luminosity of the galaxy decreases, the mean metallicity of that galaxy also decreases. It's a very nice plot showing all classical dwarf galaxies and the less luminous systems here. And if you do the same now with the position of the knee in Fe on H, you also see this beautiful correlation with the luminosity. So this goes to saying that basically the luminosity or the mass, or at least the stellar mass of these systems, is really tells you the ability of that galaxy to create metals and to hold on to them. So it's an interplay between the star formation rate itself, that may also be regulated by supernova feedback and galactic winds, but also by the galactic winds themselves that may also expel the metals you've just produced. Yes. The last point that I wanted to make on this here was that there are in most of the higher luminosity systems, so Sagittarius, Fornax, Sculptor, there is almost no dispersion around the trends that we observe besides the observational error. This breaks down when you get either to very low luminosity systems. We know that from ultra-faint dwarf galaxies that tend to show quite a lot of dispersion. And it's already the case for sextants here. And the dispersion also and this is probably due to the fact that star formation in these smallest systems is so episodic and has such a hard time to establish itself that the galaxy actually never keeps pockets of different evolution of the chemical evolution at the same time within the galaxy. With Carina, what we see here is the direct effect of the different peaks of star formation. I even have a plot that I didn't put in here, but that we see that if you plot the sequence with age, you actually see that the different peaks don't lie in the same place in that diagram. And I did keep it in. Good. And yeah, to show this, so in galaxies where you have no dispersion like Sculptor, if you look at the alpha of Refi, and you now put the ages, you see just the evolution of the age. So supernova start after some 1-2 gigayears after the start of star formation. Same thing for Fornax, but for Carina, you see that things are completely different. So old stars, all the way to green color, they tend to show a decrease here. And then when you go to dark green and blue, suddenly the alphas go up again. So that's a new star formation episode that produced again massive stars and re-lifted the alpha elements. I see a lot of frowning people. No, no, no. So it's always. Oops, sorry. So the y-axis is always alpha over Fe, always. The age is always the color, okay? So it's alpha over Fe as a function of the metallicity, same as the previous plot, but just the color code is now the age. And you see, when the galaxy has a single burst of star formation, you have a single trace. When it has two bursts of star formation, you have one trace, then up, and I don't know if there's a second trace or something else happens, at least. So I find this really beautiful, actually. But there is not a drop, so like in Carina. So indeed, when you look at it, I mean, I think the error bars are not so different in these two plots, and you see that here is more dispersed than here. And the big difference is that Fornax has each time has really a lot of star formation that then averages out in this kind of plot. So I think I'm going to spare you the yaw process because otherwise we never get to weave. And so some takeaway messages from this galaxy evolution at the smallest scales seen from the empirical point of view. What we see is that the chemical evolution of dwarf galaxies seen from the alpha element is consistent with a less efficient enrichment, which is linked to the low efficiency of the galaxy to either retain metals or to produce them. So the mean metallicity and the position of the Ni in alpha elements correlates with the galaxy luminosity. And what we see also is that when the star formation is extremely low or extremely bursty, then the dispersion is increased. We see also that all classical dwarf spheroidals, I haven't spent a lot of time in there, but they all show also the production of S process by AGB stars, which means that their star formation history or their chemical evolution was long enough to really incorporate also these products. And following the evolution with ages rather than just chemical clocks helps us understanding the timing. And in particular, I showed you what it can be used to understand which elements are created in which other sites than massive stars. How am I doing with time? I think okay, let me go very, very quick on this. I want to move now to the new era in which we are going, which is to use basically the beautiful data that Gaia is providing us with. And I'd like to explain to you a bit what we try to do with Weave. But before that, I just want to give you one example related to what we saw before, which are the dwarf galaxies. So a while ago, and these are old transparencies. They are transparencies from, I think, 5 or 6 years ago at least. We were given this expectation for the performances of Gaia in terms of parallaxes. And I had made the exercise to see what this meant in terms of relative errors, or in terms of errors for not the stars in our own galaxy, but for the satellites. So I looked basically at 50 kiloparsec, 100 kiloparsecs, at different magnitudes, what would be the errors in kiloparsecs of the errors of Gaia in parallax. And it's a disaster. The reason why it's a disaster is because, of course, the Gaia parallax errors, they grow with magnitude, but mostly the impact of an error in arcsecond is directly linearly larger at larger distances. So my conclusion at that point was that parallaxes were not competitive to measure the distances of those spheroidals because we have much better other means to do it, but they could be useful for sorting interlopers. And the reason is that if you look at 5 or 10 kiloparsecs where the foreground is, then you start to have things that are detectable from the point of view of parallaxes. More interestingly, what we always knew was that proper motions from Gaia, and again, this is now performances expected in kilometer per second as a function of the magnitude. And basically, all the way to 100 kiloparsec, you would have possibly interesting velocity precision from the proper motions of Gaia. And my take at that time was that we could expect to have mean transverse motions in some of the well-placed systems to something like 5 kilometers per second at 100 kiloparsecs. Now is Gaia Dia 2. So let's look at Sculptor. So I did the same. I kept my text of a long time ago, and this time I've put in yellow what actually has happened. And so for a galaxy like Sculptor, this is what Gaia sees. So you see that we see the stars in Sculptor all the way to the horizontal branch and even a bit below. Wow, good, huh? With proper motions, this is now proper motion in mu delta and mu alpha, you can now sort out the interpolopers by just looking at the proper motions, and you can do this potentially out to the tidal radius of Sculptor. This is working. I was expecting to see more than 1,000 stars in Sculptor from Gaia. And in fact, there's in the catalog of the Gaia collaboration and Helmi 2018 paper, there's 1,500, almost 1,600 stars. And with motions with this kind of accuracies, you could get the mean motion and the orbit of the satellite, and this has been done. The hope was that in a galaxy like this, that is well populated in Gaia and for which the brightest stars are quite bright, the internal errors of individual RGB stars could be good enough to constrain the velocity anisotropy. And this actually has been already done from Gaia DR1, doing proper motions combining Gaia DR1 and HST by Massari in 2018. And I presume there will be some updates of this very soon that I've not yet seen from really Gaia DR2 alone. This velocity anisotropy is something very important to break the degeneracies that you have when you try to convert the velocity dispersions profiles that you see in dwarf galaxies into masses. So it's a very fundamental and important thing. You could also try to separate core from cusps using these 3D velocities. These were predictions by Evelyn in 2015, and this I've not yet seen coming. And you could also potentially detect rotation, but this time in 3D. And this, again, has been done already by Massari. And so I think this is a transparency that kind of show that Gaia really, even at DR2, which is far from being the final data release, is just an amazing tool for not only our galaxy, but also the local group. And to illustrate this one last time, this is for the dwarf galaxies around the Milky Way, a nice animation that was made as part of this Gaia collaboration Helmi paper, showing the different orbits that were integrated backward in time of the different satellites in around the Milky Way. And I think you will agree that it's really very impressive and pretty to see how nice these things are. And by the way, this will also change a bit our views on how many of the dwarf galaxies around the Milky Way are really in a plane or not, and how thick that plane is, and so on. Because some of the surprises were that some galaxies that lie today in the plane actually counter-rotates compared to the others. So now the very last part of my talk, I'll try to be a bit quick, is that Gaia does a lot by itself, but it also needs to be complemented by spectroscopic data on the Earth, and I'll explain to you in a second why. And what I will be talking about is the WEAVE project, which is a collaboration between all these colored countries here, and you recognize yourselves, of course, here and there. The idea is to make a new MOS facility that will go on the WHT. This is very important because it's one of the very few projects that will be doing this in the Northern Hemisphere. And it's actually the only project that has high resolution that will do this in the Northern Hemisphere. So the basic idea is that Gaia's reach is 1 and something billion stars within that magnitude range. But there is not the full complexity of the Gaia, or the full richness of the Gaia information is available for everything. At these magnitudes, what Gaia gives is distance, well, parallaxes, proper motions. The onboard spectrophotometry allows you to get very nice stellar parameters, but for brighter stars. And for still brighter stars, there is also a radio velocity measurement machine on Gaia, so a spectrograph, that allows you to give you the third dimension of the velocities, so the radio velocity, and also stellar parameters and chemical abundances, but really for much, much brighter stars. And so the idea is that from the ground, we can we can help and really release the power of Gaia also by making these things available, radio velocities, chemistry, and stellar parameters for stars that Gaia won't be doing properly on board. So the first motivation is, in fact, to enlarge the volume in which the Gaia transverse motions are useful. So basically, you have proper motions to transform them into kilometers per second. You need to know the distance. And if you do the exercise, you see that, in fact, the errors, in the error budget of the transverse velocities, what dominates is always the distance error, always. And just to give you an idea, this is a main sequence turn-off star, this blue thing. And so as soon as you reach 4 kiloparsecs, you are basically above 40 kilometers per second error on your transverse motions. And this is because of the error on the distance. And it's even worse. I mean, it's better, but you also want to go further with tracers that are like a red clump star. You reach at 8 kiloparsec, you are again at velocities errors that are quite large. So the idea is that if you can use stellar parameters to then use isochrones and things to get spectroscopic distances that are then the error of which are independent on the distance, contrary to the distances, the parallax distances, which error grow with the distance, then you are making things much better. And this is what is shown here. So the example of the red clump star here with the transverse motions and the parallax coming from Gaia, so distances from parallaxes, gives you basically, you can't go much further than some a bit below 10 kiloparsecs. And now if you assume that you know the distance error from another source, with zero error, you get this pink curve. And if you assume it, I didn't plot it here, but if you assume some distance error that corresponds to spectroscopic typical distance error, you will get something that has the same shape, but that is a bit below. And the reason it has the same shape is that the error on distance is constant with distance. And so really the idea is to enlarge the volume in which Gaia is useful, because you see that in large volumes, the proper motions can give very precise transverse motions if you have another source of distance. We also want to complement Gaia with accurate radio velocities where Gaia doesn't have it, and this is what defined the low-resolution mode of weave. And we want to enrich the Gaia catalog with detailed chemistry for even brighter stars, and this is what defined the high-resolution mode of weave. And this is kind of bringing together these three things. We want to have radio velocities much deeper than what Gaia has on board. We want to have chemistry very detailed, and we want to do this in a large volume. WEAVE is also the first large spectroscopic survey that will be able to select its sources directly from Gaia catalogs. All the previous surveys, RAVE, Segway, Apogee, and whatnot, Lamost, always had to rely on other things and hope that Gaia would come in the future. We are in a different situation. Gaia DR2 is out, and we want to make the best use of this data to make our survey useful. And so among the 7 different surveys that we will be performing, the 2 most fiber hours consuming are the Galactic Archaeology ones and the the follow-up of LOFAR sources on the other hand. And the Galactic Archaeology survey looks like this in a galactic LNB plane. So we have a low resolution survey of all the high latitude parts of the galaxy. We have a low resolution survey confined to the plane of our galaxy to understand exactly what Elena was talking about yesterday, about the details of asymmetries in the disk, and make really tests of fundamental gravity, let's say, or disk dynamics in that range. And then the black points all over the place is the high resolution survey, and then all the colored points here are clusters, plus a few dwarf spheroidal galaxies up there. The high resolution survey has as an idea to, of course, enrich the catalog in chemistry, radio velocities, astrophysics parameters, and the idea is to combine the spectroscopic information together with the Gaia distances in the volume in which the Gaia distances are the most precise, to be able to constrain ages of individual stars as precisely as possible. And this is to constrain the assembly of the Milky Way disk mass with time this time, and not with metallicity or with I don't know what. We're having really directly time measured. And the other big science case for the high-resolution survey is to use the chemical information to do labeling, tagging, whatever you want to call it, but to deconstruct the stellar populations that we see in the galaxy. And we want to do this using elements of all different nucleosynthetic channels to maximize the parameter space. And this is what the high-resolution baseline survey looks like. What I just want to point out is basically in a lot of different places in the sky. In total, is going to be 1.2 million stars, brighter than the magnitude 16. And the very the particular thing about the weave selection is that we are going to be using the Gaia absolute magnitudes to select our targets. And this will be the first time that a survey does something like this. So we keep our fingers crossed. Sorry. The low resolution survey, the main idea is to get the transverse, the radial velocity, some information about the chemistry, less detailed, and to use the stellar parameters to enlarge the volume in which we have useful distances. One of the most prominent science cases is to understand the galactic halo from that survey, and to understand precisely how it was assembled, by how many, from how many mergers and so on. And we think that that phase space is great to do this. I mean, these are early simulations of Amina showing that in phase space, indeed, when you merge satellites, you find them back again. However, there's been a lot of work recently that show that the effect of merging satellites onto an existing disk also disturbs the in situ stellar population and produces clump in that same plane that are very similar. These are in situ stars. And these are the stars that have been accreted by 10 small satellites coming in. And you see that there are clumps here, as you expect, but there are also clumps in the in situ population that responded to the merger. And so what we think is that with a survey like WEAVE and adding the chemistry and to the information to the thing, because of all of what I've been telling you before on how individual signatures the dwarf galaxies have because of their internal evolution, then we can retrieve much better not only how many clumps or things like this there are in phase space, but also what progenitors they come from. And that's a very important part of it. And this is what it looks on the sky. So it's essentially all of the high latitude sky, the yellow thing here. In total, it's 8,500 square degrees, so it's huge, down to magnitudes 20 or 21. This is observed we've combined with some other surveys, essentially with the LOFAR extragalactic survey and the QSO cosmology surveys. And the outcome will be that number of stars, which is in this case something like 500,000 of stars of the galactic halo, not quite, and more or less the same number in the galactic disk. And in addition to this wide area survey, we're also going to follow up some of the known substructure, streams, and dwarf galaxies with an even deeper kind of magnitude, depth. And just to say this, actually one of the two leads of that high latitude survey is Giuseppina. And if you have not yet been in contact with her and are interested by this kind of science case, I mean, WEAVE is a very open collaboration. When you are in a WEAVE contributing institute, you can join WEAVE, you should join WEAVE. And it's going to be a very interesting endeavor. And yeah, I think it's going to be really a lot of fun. Altogether, it will be something like 3 to 4 million stars. To combine with Gaia and understand the evolution of our Milky Way. And with that, I leave you.
Okay, it's a little bit late, so we have time for a couple of questions.
Very nice. So I wonder if there is already a kind of indicative message for, based on the archaeological studies in the galactic and local group for the Lambda CDM model.
Sorry, there was too much noise. I didn't hear what you said. Could you just repeat?
So do you already have some indicative message based on the archaeology studies for the Lambda CDM model?
I still don't get the question. Some indication of what?
Some message based on your studies, based on the archaeological studies. Do you have any kind of message for the Lambda CDM model? Can you say something that why the Lambda CDM does not work on small scales?
Okay. I think that one of the questions that I've not mentioned here, but has been there in the literature for quite a while, is whether, given what we see of the chemical signatures of the surviving dwarf galaxies, if you accrete similar things early on the Milky Way, can you get what you see in the Milky Way halo? And the answer is still not, to me, completely clear, in the sense that if you wait until they've accomplished their own internal evolution, it's clear that if you merge something like this, you don't make the galactic halo. If you accrete them early enough that they've only started their internal evolution and have not differentiated so much, perhaps you could make some of it. Now also from the Gaia GR2 data, there's been this very interesting finding of blob or Enceladus structure that kind of brings together also a tiny fraction of the globally of the halo. It's a tiny fraction of stars that are in chemistry space follow something like a galaxy that would be more or less SMC mass or something like this. And so, it's difficult at this point to make a very strong statement saying, no way, this cannot be done this way. But it's still disturbing that the thing is still a bit contrived. Yeah, you have to merge all of the small things really very early on, and then you have one that may be of higher mass and merged more recently. But all of this together, I think we are not yet in a position to make a complete census of this.
Yes, thank you very much for the talk, very nice. Regarding the dwarf galaxies, when you talk about some of them having recurrent star formation, or can you spatially resolve it?
Spatially resolve?
Yes.
So.
So you know
there's
that
a lot
some star formation happen in this area and this other, or no? Just something that you measure globally.
No, so okay, for the smallest system that go just on and off very locally, I don't think we have any trace of how this goes spatially, because this typically happens in systems that have so low luminosities that it's just very hard to resolve things like this. When you think of ultra-faint galaxies, there is I don't know how many members there are in total, but I mean, to separate this spatially, I think we're not there at all. Then, in something like Carina, which is a bit more interesting in a way, because it's each of the three subpopulations have enough stars that you can actually look at how it goes. There were some claims that perhaps some of the spatial structure was related to basically that the ages of the stars were not spread in the same way on the galaxy. I'm not sure whether everybody agrees on these statements.
Do you know what caused this recurrent star formation? Because these are small systems.
What do you mean by recurrent in this case?
Repetitive star formation.
Like Carina?
Yeah.
Three bursts.
Yeah. What could cause it?
Cause
in some
it.
cases you don't see that. In some others you see that it's star formation.
I mean,
then
all
it
in
can
all,
be
in these galaxies that are satellites of the Milky Way, it's a combination between the internal processes and the environment.
might tend to be the most massive ones, this repetitive star formation,
No.
or no?
No. I mean, around the Milky Way, of repeated ones, there is one example, it's Carina. And then just to go a bit back to this also, I mean, I was talking about the two populations in Sculptor. This is clearly separated by metallicity and by age. So indeed, you see two populations that are spatially not the same. They are not two separated bursts of star formation, but they are two parts of the episode of star formation, obviously. So I mean, there is something going on, like, you know, you first form stars perhaps a bit too efficiently, then there is some gas going away, then at some point restarting a bit. But then if all of this happens at very old ages, the star formation histories we derive don't have quite the resolution to separate them into bursts. They're more like really two overlapping population in age, but there is an offset in the age of these two populations for sure.
Okay, we have final question.
In almost every galaxy. Sculptor was an example, but we see it in almost anything. Also, I mean, Fornax is also a very good example where you have this very recent, much more recent star formation that is not spread out in the same way as the old population.
Oh, over here.
Yeah.
Thank you very much for the talk. It was very interesting. And I wonder if you were using also non-LTE corrections or some diffusion models in these dwarf galaxy studies and so.
So in everything that I've showed here, not. We take care, not, depending on which elements, to be honest. But the selection that I showed here almost didn't have problems with non-LTE corrections in the giants in which we look at them.
Okay, so you didn't expect that many changes?
No, except for, but there are some elements for which it's important. For example, I think there was the manganese was in one of the iron peak elements that I didn't comment on so much, but there is non-LTE corrections that are very important. And also this might also impact a bit what happens at the lowest metallicity where the non-LTE are more pregnant. Yeah.
Okay, I think we have to stop here, but there is coffee served in the cafeteria, so you can keep
Coffee time.
with the discussion there. So thank you very much.
Thank you.